Alright, so now we need to figure out, just to remind you what we're doing is we're analyzing this problem here. This is a 3-wire single phase circuit, and I've got 3 loads, but now I've also got finite impedance on my wires here, and we're going to determine the power delivered to each of the 3 loads, and then determine the power loss in the wires. Alright, so that's what we're going to do here. Now to do this, we're going to basically just have to kind of go through some analysis here, and the one that makes the most sense to me is loop analysis. Now you can use any of our analysis techniques. This is again just kind of steady state analysis, which is what we kind of started introducing early on in this module. And the reason I do that, if I start trying to count up my nodes, even if I know the voltages at particular nodes, you can just see the number of nodes I have here is a significant number of nodes compared to the number of loops. So loops to me make the most sense because it's going to be the fewest number of equations I have to write, which is going to be, actually this is just one node here, but it's still going to be the fewest number of equations to write. And they're not going to be that difficult to write. So let's go ahead and label these currents I1, I2, and then I3. And so let's go ahead and now start writing our loop equations down. So let's look at loop 1 here. Well, I'm coming in on the negative side here. Well, before we do that, before I come in on the negative side, let's remind ourselves, doing all of these impedances here, we need to put these in rectangular form. And of course we know if it's at an angle of 0 degrees, just to remind you, to put it in rectangular form, you'd have 115 cosine of 0 degrees plus j 115 sine of 0 degrees. I mean, that was all the way back in the first module for this course on how to do stuff with complex numbers. But if you do that, of course, you just wind up with 115. So as far as the rectangular format here, this is just 115 volt RMS, and this is just 115 volt RMS. Alright, so now, as I said, we're going to just go ahead and do our loop here. Well, I'm coming into the negative side here. So if I'm coming into the negative side, that means I'd have minus 115, and then I have plus 1 times I1, because that's for this resistor right here. Oops. Didn't mean to erase the resistor. And then I've got this 50 ohm right here. But if I do the 50, I've got 2 currents. Now I'm in loop 1, so I1 we know is positive. I2 is going in the opposite direction of I1, so it's I1 minus I2. And then we have plus 3, and again I've got I1 is always going to be positive because I'm in loop 1. But then I1 and I3, I think of, if I look at the resistor, they're going in opposite directions. You might say, no, they're going in the same direction. They're both going clockwise. But when you want to look at it, you want to look at the diagram as far as, okay, the arrow means I1 is flowing this way through the 3 ohm resistor. And if I follow the arrow here, I3 is flowing in the opposite direction of the 3 ohm resistor, of the I1 here. So that's why we get I1, of course, minus I3. Now this is all stuff we learned back in Circuits 1, but it's always good to kind of remind ourselves why we get particular values that we do. And then this is equal to 0. And then of course we can just kind of simplify this equation. So if we do this, we'd get I1 plus 50 I1 minus 50 I2 plus 3 I1 minus 3 I3 is equal to 115. I move the 115 to the right hand side, and then combining like terms, I would wind up with 54 I1 minus 50 I2, I don't know why I put that so far apart, minus 3 I3 equals 115. And so this would be equation 1. Alright, so I'm going to kind of scroll back and forth here because I don't want to necessarily erase this. So then I have loop 2. So if I come back up here, loop 2 is this loop over here. And so I can start anywhere in the loop. So I'm just going to start at the 20 ohm resistor. No reason, I just decided to start there. So I would have 20 times I2, and then I have a J10 ohm inductor times I2. And then I'm going to flow around here to this 100 ohm resistor. But then again, thinking about I2 and I3, I2 would be going up, I3 is going down through that resistor. So we'd get plus 100, and I'm in loop 2, so that's the positive one. They're going in opposite directions, so I have minus I3. And then finally, I would get plus 50 I2 minus I1, and this is all equal to 0. And again, just like we did before, combine like terms. So I have 20 plus J10 I2 right now. I'll just factor that out. But then I got plus 100 I2 minus 100 I3 plus 50 I2 minus 50 I1 equals 0. Now let's finish combining terms. So I have 100 plus 50 plus 20. So that's going to be 170. But let's write the I1 first. So I have minus 50 I1 plus 170 plus J10 I2 minus 100 I3 equals 0. And so this would be my equation 2. Okay, so now, of course, we still have one more equation to write for loop 3 here. And again, it doesn't matter where to start, but I always typically start with a power supply when there's a power supply present. And so the arrow is going into the negative side, just like it was in loop 1. So for loop 3, I'd have minus 115. And then if I go back up here, I'm going through this 3 ohm resistor, and I've got I3 and I1 in opposite directions. But because I'm in loop 3, I3 is positive, and then it would be minus I1. And then finally, my next term would be this 100 ohm, and again I have I3 and I2, so that would be plus 100, I3 minus I2. And then finally, I have this 1 ohm resistor that I briefly scrolled back up to, so I'd have plus 1 times I3, and this is all equal to 0. And then multiplying things out again, just like we've been doing all along. And now, of course, I've just combined like terms and write it in sequential order again. So I'd have minus 3 I1 minus 100 I2 plus 104 I3. And this would be equal to 115. So that'd be equation 3 then. And so now we get to go use a calculator to solve these using the matrices, because I got 1, 2, 3 equations and 3 unknowns. So I'm going to go ahead and pause the video here and set that up and then continue the recording. Okay, so then again, you can find this link within our Blackboard site. Again, if you might have a calculator that can do this, but if you don't have a calculator that can solve this matrice, went ahead and typed it all in here for you. I haven't solved it yet, but then I'll go ahead and get it to solve it here. Maybe. It's thinking. There we go. Oops. So it went ahead and solved it for us. And of course it's doing something stupid and giving us some really huge numbers here. And I'm just wondering if there's a way for us to find that, if it wrote it in decimal anywhere for us. It wrote some of the numbers in decimal for some reason, and some of the other numbers not in decimal. So for some reason it didn't want to write these here in decimal. So we'll go ahead and copy those back in decimal format here. So again, I'm going to just pause the video here and copy these back into our other screen here. So it's going to flash back to the screen here, but there's no point in recording the video while I copy these numbers back. Okay, so I've gone through and, as I said, just copied those numbers back into the circuit here. So we've got I1, I2, and I3 now. Let's go back again, remind ourselves, what are we trying to determine? It says determine the power, and I'm actually going to say, determine the power. So we're actually going to determine, all of the power here, so like average power and any kind of reactive power, because we have here a load here. If we combine these together, this is 20 plus J10. So there's going to be average power and reactive power there. Alright, so let's go ahead and compute all of those things. And we have this current here in magnitude form. So the nice thing here is that if we're looking at the magnitude of these currents squared, it will be very easy for us to compute these here. So let's first go ahead and look at the power for the 20 plus J10 load. That's a pretty easy one for us to do because of the fact that we know that the current through that load is simply I3. And remember, we have here that power is equal to the magnitude of my current squared times the impedance. And remember here, this value right now, this is the magnitude of I, which is convenient for us. Now, I'm sorry, not P. We're talking about complex power, S. And remember, this unit is volt amps. Now, one thing we should remember here is I just said I squared I. There's also another formula from the previous modules where it was 1/2 I squared times Z. Why don't I have the 1/2 here? Well, again, let's go back here, and these are RMS values. So maybe what I really should have done here when I wrote, and I only wrote one of the units out here, amps, I should have written amps RMS, because these are all RMS values then. So that means we don't have that 1/2 in front like we do when we have non-RMS values. Okay, so for the 20 plus J10 load, we would have S is equal to 10.37 quantity squared times 20 plus J10. So I'm going to do that real quickly on my calculator in front of me. And I made a mistake here. When I was putting into the calculator here, it's I, but I should be careful. It's not I3. It's I2. I didn't carefully look at my graph here. I was thinking that I'd label this I3, but that's I2. So let's go back and fix that here. So it's I2, which is 9.39 and an angle of negative 24.5 degrees amp RMS. Okay, so then this would be 9.39 squared. So let's do that computation. And if we do that computation, I get 1,763 plus 881 J volt amp RMS. Now what that means here is for load 3, because I believe I labeled that one load 3, which is probably why I got confused with it being the current there. So for that, that means the power, the average power for load 3 is 1,763 watts, and we do have some complex reactive power as well. So Q3 for that would be 881 var. Now we can go through and compute the rest of these here. So if we want to compute the rest of them here, for instance, if we look for load 2, I guess we'll just go backwards. Load 2, I want to be careful here. The current through load 2 is actually like I3 minus I2. So I'm going to look at what is the magnitude of I3 minus I2. Or actually, instead of looking at what the magnitude of I3 minus I2 is, let's just go ahead and do that computation. Now, I again like to do that in rectangular format for adding and subtracting. So I'm going to say I3, which is 9.63, minus J 3.85, minus 8.55, minus J 3.89. It's I3 minus I2. So if we did that, we'd wind up with 1.08 plus J 0.04 amp RMS. And this is equal to 1.08 at an angle of 2.12 degrees. So for load 2 then, if we think about, well, I could put S down, but there's only a resistor, so I'll put just P. So P2 would be the magnitude of I squared times my load, and in this case it would be 1.08 squared times, I have a 100 ohm load, which gets me 117 watts. Now for load 1, we're going to do the same thing here. I'm just going to kind of skip a tiny bit here on some of the work as the video is getting quite long here. But we would get here, the current through this would be simply I1 minus I2. And so we would have that the power through load 1 is the magnitude of I1 minus I2 squared, which, here I'll just write off what I1 minus I2 is. I'm sorry, it wouldn't be I1 minus I2. I keep mixing up my loops here. No, this would be, I'm sorry, that I'm 100% correct. I don't know what I'm doing right now, I'm sorry. I1 minus I2 squared times 50 ohms. And if we do that, we get 206 watts. So if we add those up here, the total average power to the loads is just adding those three numbers up. 2,086 watts. So that's the total average power to the load. Now let's look at the losses here. Now I didn't show you the computation for that. Well, the losses here, well, the current, this is simply equal to I1, because let's go back here. This current would be IAA. IBB would be this current, and then that's the neutral current here. So the neutral current would be I3 minus I1 for the neutral current. So IAA is just equal to I1. Whoa, I don't know what just happened there. Which is equal to 11.24 at an angle of negative 19.83 degrees. IAB is actually equal to, it's technically negative I3, but the negative I3 really just gives you a phase shift. So we will also wind up with 10.37, but then instead of being negative 21.8 degrees, we get 158.20 degrees. Now you could verify that on your calculator, but it is negative because it's going in the opposite direction. And then my neutral line, if I do the subtraction of I3 minus I1, what I wind up getting here is 0.9459 at an angle of negative 177.7 degrees. Okay, so those are the three currents here. So my losses here would be, well, power AA would be 11.24 squared times 1 ohm, which gets me 126 watts. Power in line AB is equal to 10.37 squared times 1 ohm, which is equal to 108 watts. And finally, the power loss in the NN is going to be 0.9459 squared times 3, which is equal to 3 watts. Okay, now I know this video is getting long, I apologize for it, but I'm going to make a few more comments here. So we said that, hey, this is a pretty long example we went through, and we said we don't have this nice kind of balanced load here where they're both the same. You know, there's two different kinds of loads going on there. But when it's balanced, what did we say? How much current went through INN? We said, well, there's zero current coming through the neutral line. Well, if we come into the situation where I'm not balanced here, I still get a very minimal amount of current coming through there. I mean, yes, it's almost an amp, so that's a lot of current, but compared to the 10 and 11 amps, that's small. So look at how much power you're dissipating on the neutral line versus how much power you're dissipating on the actual power lines, the hot lines. But if we add this up, we get a loss here. So we have a total loss of 237 watts. Now, if you're wanting to talk about the efficiency here of this, which is this kind of weird Greek, almost looks like an N, total power delivered total power generated. Now we're talking about average power in this case. We're just talking about the efficiency of the average power. We're not including the volt amp reactive component in this. And so this would just simply be 2086 over 2086 plus 237, which is equal to 89.9%. But you might think this is a pretty good efficiency for like a distribution for power lines, but it actually is not. This is actually not a very good efficiency. Power grids want to even have better efficiency than this. Now for generators, this would be an amazing efficiency for generator. You know, that you're getting this much power out of the generator versus what you're putting into it. As far as the total power delivered versus the total power generated, because there's a lot of heat in power generators and other losses that you get when you're generating power. So this would be unbelievable for like a steam power generator. So this, I know, was a long example, long problem here, but I wanted to go through it to show that while we have these 3-wire single-phase systems, we shouldn't think about these as being complex. We just apply all of the circuit analysis that we're used to applying to analyze them. All right? So after this, we will now dive into 3-phase systems.